In algebra, we discuss functions that map the set of real numbers onto the set of real numbers, or onto a subset of the set of real numbers onto another subset of the set of real numbers, depending upon the range in the domain. In calculus, we talked about functions that mapped two space onto the set of real numbers, or functions involving two variables. We also discussed functions that involved three variables. In today's lesson, we're going to start talking about functions that map one vector space into another vector space. T colon v arrow w denotes a function that maps one vector space v into another vector space w. Now, if v is a vector in vector space v and w is a vector in vector space w, then we write that v as a function of t is equal to w. The vector space v is called the domain of the function, and the set of all w such that tv is equal to w for a v in the vector space v is called the range. So let me point out some of the things we're talking about. We have a function that maps a vector space v onto a vector space w. V is called the domain. The subset of w for which the vectors in w have a corresponding vector v in the domain is called the range. So the range does not necessarily have to be w. The range could be a subset of w. But it's the set of all vectors w, so that the vector w has a match back in the vector space v. Now, this vector w is called the image of that vector v. So this w is the image of v. V is the pre-image of w. Now, I've written that down for you in the notes here. So w is called the image of v, and v is called the pre-image of w. The function t that maps a vector space v into the vector space w is called a linear transformation if the following properties are true. The first property, t of u plus v is equal to t of u plus t of v. T of cu is equal to c times t of u. In other words, the function of the sum is the sum of the functions, and you can factor out your constant. If it satisfies those two things, then it's called a linear transformation. Determine whether t mapping 3 space into 3 space defined as t x y z is equal to x plus y, x minus yz is a linear transformation. Okay, since we're mapping the 3 space, we'll let vector u be A, B, C, and vector v be D, E, and F. And we want to show that T of u plus V is Tu plus TV. So I'll start with T of u plus V. Now I'm not going to bother to put the vectors over u and v. I can't bold them with this, but just we're talking about vectors u and v. Well, this would equal to T of A, B, C plus D, E, F. Which is equal to T of A plus D, B plus C, B plus E, C plus F by vector addition. Add the components. A plus D, B plus E, C plus F. Now by the transformation it was x plus y, x minus y, and z. So do the x plus y, A plus D is in the x position, B plus E is in the y position, C plus F is in the z position. So it would be x plus y would be adding these two. So that would be A plus D plus B plus E. X minus y would be A plus D minus B minus E. And of course Z is still just going to be C plus F. Now you're probably thinking, how are we going to put these things together to get what we needed to have? What we need to get is Tu plus TV. Well, really, I'm going to cheat a little bit. And I'm going to come down and I'm going to put Tu plus T of V, which would equal to T of A, B, C plus T of D, E, F. Now my transformation said x plus y, x minus y, and z. So when I do t on this, it's going to be A plus B, A minus B, C, plus, this would be D plus E, D minus E, F. By vector addition, this would be A plus D, it's going to be A plus B plus D plus E, A minus B plus D minus E, C plus F. And notice that they now meet. These are the same. So by the time you put the two parts together, it looks like I worked it straight through. So I proved the first part. Now for the second part. I've got to show that T of CU is C times T of U. So here, since I'm using C as a constant, we'll let U be something else. Say let U equal to x, y, z. Then t of cu would equal to t of c times x, y, z, which would equal to t of cx, cy, cz, which is equal to cx plus cy, cx minus cy, cz, which is c times x plus y, x minus y, z, which is c times t as a function of x, y, z, which is c tu. So therefore we proved the second part. So it is a linear transformation. So to determine whether it is a transformation, the answer is yes, because we've proved that it satisfies both conditions. Now I'm going to just give you some properties of a linear transformation. All the proofs are quite simple. Some of them you'll be asked to prove in your exercises, and some of them are in your book or any reference book that you'll find. So the properties of a linear transformation. The first, t of 0 is 0. Second, t of the opposite of v is the opposite of tv. Now if you think about this one, if we put a -1 here, that's just really the same thing, just factoring it out. T of u minus v is tu minus tv. Again, think of this as being u plus the opposite of v. That works right through. And t of c1 v1 plus c2 v2 and so forth is c1 tv1 plus c2 and so forth. So all we're doing is just combining properties 1 and 2 that we proved earlier. The transformation of the sum is the sum of the transformations, and also you can factor out your constants. So it's really just straightforward. Determine whether T, mapping 2 space into 2 space, defined by T as a function of V, is equal to the matrix 0, 1, 1, 0 times V, is a linear transformation. And then evaluate TV for V is equal to a -2, 3. Now notice we're talking about 2 space. So we find out if it's a linear transformation. I need to see if it satisfies the 2 conditions. The first meaning that T of u plus V is equal to Tu plus TV. So we need to check that out. So to go back up here and work with it to see what this thing really says, I'm just going to let V equal to x, y. So T, V would equal to T of x, y is equal to 0, 1, 1, 0 times x, y, which would equal to, that would be 0 plus y, x plus 0. So we see that t of xy is really yx. So now, going back up to the u and v, we'll let u equal to AB, let v be CD. Then t of u plus v is equal to t of AB plus CD is equal to t of A plus C, B plus D by the vector addition, just adding the components. Well, my transformation is really t of xy is yx, so I'm just changing it. So this would be B plus D, A plus C. Well, if we want to try the same trick we did a while ago, to see if this would be t of AB plus t of CD, which remember this would be t of u plus t of v. If we go back up, this would be just reversing it, so t of AB is BA, t of CD is DC. So one step to add these, this would be, well, I don't need the step because I already have B plus D, A plus C. So we have the proof of that part of it. Now the second thing we had to show you is that T of CU is equal to C TU. Well, we'll let U be AB. So T of CU is equal to T of C times AB, which is equal to T of CA CB, which is CB CA, because remember the transformation is defined as T of xy is yx. This would be C of BA C times BA, which is C times the transformation of AB, which is C times the transformation of U. So, I said determine whether it is a linear transformation. The answer is yes. Now we said evaluate for v is equal to negative 2, 3. But notice what it does. It just turns it upside down from xy to yx. So then that means t of a negative 2, 3 is going to equal to 3, negative 2, or I could write it in column form as 3, negative 2. Now I'm going to give you the general statement for the particular example that we just looked at. Let A be an M by N matrix. T mapping N space into M space, defined by T as a function of V is equal to AV, is a linear transformation. In other words, TV equal AV will define a linear transformation if I'm using matrix A, which is M by N. In order to allow matrix multiplication, the vectors in N space, that should be N space, are N by 1, and the vectors in M space are M by 1. Now, to show that something is a linear transformation, we must show that the two conditions of a linear transformation are true. In other words, we must show that T of U plus V is TU plus TV, and that T of CU is C times T of U. Well, T of U plus V will equal to A of U plus V, that's the way it was defined. Well, by distributive property of matrix multiplication over addition, that would be AU plus AV, which is T of U plus TV, which is just a straightforward proof. And same thing for the second one. T of CU would be A of CU, because we defined the transformation as being T of U is equal to AU, so T of CU would be A times CU. Well, one of the properties of matrix multiplication is that we can reassociate, so I can, rather than having C with U, I can put A with U and C outside, which is nothing more than C times T as a function of U. I got a little bit slack on doing my superscripts in my bolding, so follow along with me. T mapping R square into R square, this is 2 space into 2 space, so it should be superscripts here, such that T of 1, 0 is equal to 1, 1, and T of 0, 1 is equal to 1, negative 1, 1. Find T of 1, 4. So T maps 2 space into 2 space. And it's defined so that T of 1, 0 is equal to 1, 1, and T of 0, 1 is equal to negative 1, 1. Find T of 1, 4. Well, what I know is, I know that there's a matrix A, so that T of V is equal to AV. That's just what we proved. It's going to be a matrix A. So that T as a function of V is equal to AV. So there's a matrix A, so that T of 1, 0 is equal to matrix A. I'll just call it AB, CD times 1, 0. And this will be 1, 1. Well, using the same idea, we can see that T of 0, 1 will equal to the matrix A, B, C, D, matrix A, times 0, 1, and that will equal to negative 1, 1. Well, here I have A plus 0 is equal to 1. C plus 0 is equal to 1. Over here I have 0 plus B is negative 1. I have 0 plus D is 1. That means matrix A is going to be 1, negative 1, 1, 1. So then that means T of 1, 4 would equal to A times 1, 4. That'd be 1, negative 1, 1, 1 times 1, 4. One minus 4 is negative 3. 1 plus 4 is 5.